Thank you, James, and thank you for the opportunity for sharing our hopefully quite exciting work on validating this new platform. So, as has already been said, I'm from the West Midlands Regional Genetics Laboratory, which is based in Birmingham, in the middle of England here. We serve a population of approximately 6 million, which is roughly a tenth of the UK population. And I'm going to particularly concentrate on application of chromosomal microarray to developmental disorder cohorts. So we have implemented, as the whole of the UK has, CMA as a first-line test for all patients with developmental disorders. So for us, that equates to around about 4,000 tests per annum, with a 15% on-year growth. So across the UK, I think this probably still represents pretty much, by far and away, the single most common molecular-based test in genetics labs. We also apply it to prenatal diagnosis for structural anomalies and also to fetal pathology, but the numbers are far smaller than the developmental disorders. So just as a bit of background, really, just to fill you in the context of how we think about which platform to go for within the NHS. As a reminder, the NHS is free at the point of care for all patients. Therefore, cost, detection rate, ease of analysis and throughput are incredibly important, and we are being squeezed quite tightly. So we have to try and concentrate on delivering these factors. And though I completely agree with Midori that discovery is an important aspect of the role of clinical science, it's possibly less important than those four factors, certainly in the context of the National Health Service. And this is particularly true given the fact that we've had some very high-profile, centralised research projects, in essence, coordinated across the National Health Service. And I guess the most famous of which is the Deciphering Developmental Disorders project, which I'm sure lots of you have heard about, and there are over 10 presentations, I think, at this meeting regarding this. So in terms of the typical developmental disorder patient pathway, where does this sort of research study fit in? Well, as I've mentioned, CMA is the frontline diagnostic test, currently supplemented with single gene testing, although this was a case certainly until 2015 when the DDD stopped recruiting. So the DDD project aimed to deliver over 12,000 trio exomes of undiagnosed patients, plus ultra-high resolution array CGH back on top of the routine diagnostic testing. So I said until 2015, and post this year, the climate's changing somewhat. So CMA being still probably the frontline test, but increasingly laboratories and centres are developing application of a clinical exome, filtered clinical exome for relevant developmental disorder genes on top of the array or after the array, followed by recruitment for suitable patients to the 100,000 Genomes Project. Again, you will have heard about this project, which is a very large centralised project which has been delivered by a private, wholly owned subsidiary, rather, of the Department of Health Genomics England. So we recently were in a position where we had to think about choice of CMA platform. Our previous provider, Illumina, and previous to that, Bluenome, who Illumina bought, discontinued the platform that we've been using for the last 7 years or so. So in terms of, I won't go into too much detail about cost, but basically in the NHS there were basically 3 options available, and they are the 8x60 design, the Affymetrix Cytoscan 750K. Many of you will use the Cytoscan HD, so this is a filtered version of that, which is cheaper, and the Illumina Cytosnip 8x50 bead array. So these are really the options, and we looked very closely at all of these. So just as an aside to the DDD project, before going into what's informed our choice, I think it's fair to say this has utterly transformed clinical genetics in the UK. It's led to huge developments in Decipher, which is an amazing frontline analytical tool. It's delivered 12,000 exomes back into the NHS and really has helped to expedite interpretational skills and the birth of the genomic MDT around regional centres. It's ended the diagnostic odyssey, which Midori's mentioned, for many, many families, and discovered over 12 new genes. And also, very importantly for the array design, has resulted in a very evidence-based gene list of over 1,400 genes called the DDG2P, which is freely available to download from EBI. So in this gene list, the mechanism or consequence and HI scores are available, as HI scores being the probabilistic scoring for any particular gene of being pathogenic in a monoallelic deleted state or loss of function mutation state. And this was used by OGT to inform, OGT and Matt Hurls, to inform a new array design which became the V3 array. Also used, the other piece of evidence base was the existing ISCA gene dosage sensitivity map hosted by ClinGen now, and I've been part of the curation committee, and I know full well that at least 40% of the genes off that original ISCA design have been curated off as being clinically irrelevant. So really it is time, it's long overdue for a redesign of the ISCA gene list, and many array platforms still use that. So there's kind of wasted opportunity within those regions. Also used was the ClinVar submitted clinical cases, so those cases clearly curated as being pathogenic, and also the Decipher recurrent syndrome list as well. So in terms of a 60K design, the design the design basically looks at, and if we think about theoretical resolution with 3-probe calling, over 300 monoallelic loss of function genes are targeted at exon level, based on the annotated, the canonical or largest transcripts. In addition, DDG2P genes with a monoallelic missense or uncertain mechanism are added, as are curated Decipher syndromes at increased level, and importantly, an evidence-based backbone, which was tiered from 1 to 3, depending on the incidence of haploinsufficient genes and also reported pathogenic CNVs. So this gives us, in tier 1, a theoretical average resolution across the backbone of 120 kb, going up to 500 kb in regions where there's very few genes at all. So a highly targeted, in a way, design to maximise clinical utility. So in terms of a validation, we have a bank of thousands of abnormal cases to draw from. We really wanted to test CNVs at the limit of detection previously. For example, those CNVs with 2 probes called previously, where we've had to do additional work. Obviously, mosaics are challenging samples as well. And we had, as I've already mentioned, many samples with data of those 3 platforms there. So concentrating on challenging cases. So the first thing to look at really is the comparative quality of the array hybridization, probe hybridization across these samples. So this is just comparing the OGT V3, that should say, with the Illumina V2. And you can see a significantly lower DLR spread for the OGT probe design in comparison to what we have been using previously, which in essence will give you less false positive data. So, I mean, it's always worthwhile putting some very large imbalances across the array just to test the performance of the probes. And this is a big deletion, 8.7 megabases. I don't think any array platform would struggle to pick this up. But the important point is that the mean log2 ratio of this imbalance is minus 0.9, and every single probe within the region is below the threshold of minus 0.6. This data isn't smoothed or weighted in any way. So moving on to smaller deletions to this PDHA, pyruvate dehydrogenase A, in a female patient, and this gave us 35 probes on the V3 array, multiple exon deletion of 13 kb. There was less probes on previous arrays, and this was just to show that, yes, multiple exons can be detected very readily. This is a really important gene, which wasn't on the original ISCA V2 list, MEF2C, which is associated with the 5q13.4, microdeletion associated with severe developmental delay and hypertonia and seizures. So this was manually called originally on the ISCA V2 array, only 2 probes were in it. The analyst was very observant, and we went to take it on to higher resolution arrays to confirm it. On the V3, there's 36 probes. It gives us a minimum size of 60 kb with multiple exons. So this would have been challenging previously. Moving down a bit more, Rubinstein-Tabby deletion, again, 2 probes on the V2 array, 9 probes on the V3 array, a minimum size of 2.2 kb, 2 exons. And then MID1, intragenic duplication of a single exon. This patient's actually, the clinician was so convinced this patient had OPITS-G that as well as sequencing analysis of the MID1 gene, 3 different arrays were used over a 7-year period before we finally detected it actually on a custom OGT X array as a single exon duplication, and we validated it again on the V3 array, 3 probes, minimum size 500 base pairs. Interestingly, this was actually missed by the DDD 2 times 1 million array, just because of where the probes were placed. And you can see if we zoom in, there's where the probes are. And finally, in terms of the validation cases, this is a mosaic trisomy 18. We knew this was a mosaic trisomy 18 from peripheral blood, from an neonate with IUGR. And we looked to confirm this on a buccal swab to see what the level was elsewhere. Now, I think you probably agree that from the copy number trace, you really can't tell much of a movement up in 18. If you knew it was there, maybe you could be persuaded. But one of the kind of neat features about the OGC software is this aneuploidy summary plot, which is basically a box and whisker plot, which plots out log2 ratios of every individual probe and comes out with a mean and a median, which you can quite clearly see a rise on chromosome 18 here. In fact, the lowest log2 ratio and the highest log2 ratio are also the highest across the whole chromosome, which we do expect from a whole trisomy. So when we're doing the analysis, the first thing we do is have a quick look at the aneuploidy summary. It takes seconds, and I think anyone would immediately spot there's something strange going about with trisomy, with chromosome 18, which would be difficult to detect otherwise. So I'm going to show some validation of CNVs from the DDD project next. As I've already mentioned, this is 12,000 undiagnosed patients, trios recruited, and the majority had routine RACGH, local centres. So whole exome sequencing, ultra-high resolution carried out, wet work carried out by the Sanger Centre in Cambridge, and then plausible pathogenic variants were fed back to the local teams for validation, interpretation and discussion. So we recruited 1,200 trios from the West Midlands, so we're the single largest recruiter, and currently we have 300 variants to work through, many of which we've already reported so far. Most of these are SNVs, but there are a number of CNVs as well, which, given this slide, I'll concentrate on those. So this is the sort of report we get back. So the email and the lab get, the clinician and the lab get an email to say that there's a result awaiting for them. We go into Decipher, we pull out the result, and we can see here a summary of the patients. So there's very deep phenotyping carried out on these patients, which is obligatory for recruitment to the DDD, which is one of the innovative parts of the project to make interpretation downstream much more easy. And you can see here that a de novo variant has been reported back, 1.3 kb, one gene. It's in the DDG2P gene list. It's inheritance said to be de novo. The mean ratio confirms the fact it's a deletion, and it's a loss in hemizygous state. So then we simply go and log into the genome browser in Decipher to have a look at this variant in the context of the rest of the genome. And you can see here this very small deletion within this red haploinsufficient gene, HDAC8, takes out two exons there, HDAC8. Histone deacetylator 8 has an important role in tagging epigenetic regulation early in development. So it's a key gene. And you can see here that it's annotated to be associated with Cornelia de Lange-like syndrome relatively recently, within the last 5 years or so, which is a confirmed X-linked dominant loss of function gene. We also, I'll go back to this, if we look here, you can see we have copy number plot. If we log onto that, we get a screenshot of the Sanger's data. So I can't configure this myself. If I had done, I would have increased the dot size for you to see, but you can see here, this is the ultra high resolution 2 times 1 million adjuvant array that was carried out, two arrays, combined data. Pretty much the highest resolution you can go at considerable expense. And this shows a de novo 1.27 kb deletion here. Well, we don't know it's de novo yet. We need to validate that, but you can see this deletion here. On the exome, so this is read depth, so all of the reads from each exon have been concatenated into a single data point. You can see here that there's a drop on the proband in one of the two exons and no corresponding drop in mother or father. But I would like to suggest that this is not entirely convincing, and indeed I don't think was called routinely through the pipeline. It was called on the array-CGH. And we've already heard from Midori and many others at the meeting about the fact that calling anything less than 3 exons from an exome is incredibly challenging. So we went to confirm this. This is about 3 weeks ago with the new array. And you can see here, this is the whole gene. Right at the end of the gene here is a very clear deletion. It's 1.17 kb as a minimum, 2 exons, 7 probes. Zoom in a bit more. very, very clear. And in fact, this is kind of part of the whole validation. Did we make the right choice with this array? So we took this for a predictive comparison to the UCSC browser to see what we might have picked up using another platform. And what we can see here is that I've plotted the Illumina CytoSNP probes here as a bed file, the OGT V6, V3 rather, down here, and then the AFI Cytoscan HD. So we can see 3 probes on the Illumina and 2 on the AFI array, which even if we had this deletion spanning the entire maximum region, so the minimum size as predicted by the OGT array is here, the maximum outside of it, the other 2 platforms would not have detected this. Another case, another DDD research project report, MED13L, 3 kb, 3.4 kb, 1 DDG2P gene, de novo again, and lost heterozygous state. So MED L13 is a mediator complex subunit L1 like 13, which is very important in early transcription in the brain and the heart. Our patient's actually has not got a heart defect. Transposition of the great arteries, I think, being the particular heart defect, but has got the learning disability. So we take this to decipher. Again, we can see very small deletion of a single exon there, annotated as being associated with intellectual disability, monoallelic loss of function gene. Actually curated as being a probable DDD gene. I think most of these probables are definites now, though. So again, if we look at the exome trace and the ultra-high resolution array trace, you can see the deletion there just about from the ultra-high resolution array. A drop here, again on the proband exome, and no corresponding drop on mum or dad, suggesting it's de novo, but we need to confirm that. So if we take this to validate on the V3 array, which we did, this is according to the data we got from CytoSure, it's a minimum of 269 base pairs because some of these probes overlap to a certain extent. 1 exon, 3 probes. Zoom in a bit more there, very clearly a single exon deletion. Again, we do our comparative comparison in the UCSC browser. So there's the 3 OGT probes, the V3 probes right on the exon there, 2 probes in the Illumina CytoSNP 850K, 4 in the AFI array. Given the fact that these are high-density SNP arrays, which need a lot of probes to call, 10 or more, certainly in the case of the AFI array, this suggests that this imbalance would not have been detected on the other 2 platforms available to us in the cost bracket we want to go with. So just as a summary, these genotype-phenotype associations were discussed in the local MDT, and both de novo cases were felt likely to completely fit the phenotype. Clinical reports have been issued, and so in essence we've carried out a very rapid and cost-effective validation of these 2 research findings. The important thing is, of course, these answers would have been available for families years previously if we'd have had this array before recruitment to the DDD project. So that would have saved the whole system an awful lot of money and allowed patients with different diagnoses that we couldn't detect to be picked up through the study. But that's the way of the world and the way of genomics. So we've cautiously applied, or cautiously, we've had some limited application of looking at the higher density V3 array with SNPs added to it. And fortuitously, we were able to carry out this on an unusual case of autosomal recessive Bartter syndrome, where the clinician contacted us and said, can you do a SNP array? We've got this kind of weird homozygous deletion, which we think could be due to a UPD event because we can only find father's a heterozygous carrier and mum's normal. So Bartter syndrome type 4B is a very severe disease characterised by renal salt wasting and deafness, in type B anyway. And basically 2 very highly related genes, CCLC-NKA and B, are both involved in this. It's also recessive, so they're both deleted or mutated. There is also a less severe Bartter syndrome type 3, again with the renal salt wasting but without the deafness. And this is just mutations or variants in CCL-NKB. So we carried out an AFI array, 750K AFI array, and you can see the advantage of these SNP arrays really is the incredible power of being able to detect very accurately acquired loss of heterozygosity or segmental UPD. So you can see here from the SNPs, there's an absence of heterozygosity in these two regions. Across this chromosome 1, so two big regions of segmental UPD, AOH, within the chromosome. And you won't be surprised to know that the Barter gene is in 1P. So what we can see if we zoom in to this region of AOH is a homozygous deletion running through here. I'll zoom in a bit more. And you can see that the softwares call this deletion across the two genes, A and B. However, you look a bit more closely at it, you can see that it's difficult really to say which gene is involved in this deletion. Well, you can say that B certainly probably is, but A seems to be involved on the basis that a noisy probe, is below the threshold for a deletion outside, and the software has made a big call right across the two genes. So we really don't know which gene is deleted. We could tell the clinician there's UPD causing the event. So again, I went to UCSC browser to see what the coverage was like on other platforms, and even just putting the 60K array on, we can see that A and B are both well covered in terms of probes. So this is the AFI CytoScan HD with the small number of probes within B and none within an A. I think this is probably a consequence of the fact it's really difficult to design 25 mer probes to two genes which have got at least 90% sequence homology. It's just very difficult technically to do it. So this is the result. We've only run 8 of these samples, as I mentioned. So the OGT V3 180K SNP. You can see the two regions of homozygosity within here, consistent with the segmental UPD, and a very clear homozygous deletion down there. And if we zoom in, we can see that there are plenty of probes in A which are not deleted, and plenty of probes in B which are kind of off the scale because of the homozygous deletion. So we can say that A is not deleted. We don't expect to have deafness in this patient, and this is consistent with Barter type 3. So in summary, we've implemented this array as a frontline platform for developmental disorders, prenatal and pathology referrals, fetal pathology referrals. Prenatal, I hasten to say, with structural anomalies. Single exon deletions can be detected very readily if they're targeted. I think high density does not equate to high resolution. And of course, there is the issue of new genes and, do we need future versions of this array? However, I think if you go to Matt Hurl's talk tomorrow between 11 and 11:15, he'll try and convince you that actually the majority of haploinsufficient genes have now been discovered. So a future design would probably not have that many more genes in the design. So I encourage you to go to Matt's talk tomorrow, Prevalence and Architecture of Dominant Developmental Disorders, which is the culmination of work from the DDD project. So future improvements, OGT are very responsive to our requests, and there are a number of requests we put in for CytoSure software developments, one of which they'd already addressed by modifying the CBS algorithm slightly. As with any new platform, there are going to be some artifacts creep in with a new array design. We've seen it, and I think Chris probably has as well. So there's a small number of largely exon 1 GC-rich related artifacts, all duplications, which after you've run 300 arrays, you can cope with because you know it's an artifact. But as we have 30,000 exons, if there's 15 of them that are dodgy, we can kind of live with that. Sorry, 3,000 exons from 300 genes. The other thing we'd like to encourage OGT to help us with really is, as an NHS, we've set up a data sharing consortium via Decipher, and we're just wondering about some sort of help with an auto-upload capability to that to make our life a bit easier, because clearly, as Midori said, and I think I've demonstrated with these exon deletions, the SNV and CNV worlds are colliding at pace, and we really need to know how to interpret exonic CNVs, intragenic or intragenic CNVs in particular, in the context of single nucleotide variation and similar disease mechanism. Just to say, actually, with the CytoSure software, we were fortunate in having all of our data in Cartagena. So this is about 15,000 fully annotated CNVs with HPO terms, which we downloaded as a track into the CytoSure software in approximately half an hour. So that's very powerful as well. So we've got all of that at our fingertips too. And yeah, well, I'd like to stop there and just acknowledge all of my colleagues in the lab. Lots of people have been involved in this project. The DDD and Decipher teams, and of course the AGT team for being great in helping us implement this. So thank you very much for your attention.